Hello everybody, my name is Mohit Deshpande, and in this video I want to discuss matrices and just introduce you to the concept and then give you a very brief understanding of what they are and how we can use them. And then in the next few videos we're actually going to delve a little bit more into the different operations that we can do with matrices, and then we'll see why they're important when we discuss image processing later on. So first of all, what are matrices and why do we care about them? Well, you can think of a matrix as being like a 2D grid of values arranged in rows and columns. In rows and columns. I'm going to use calls for columns. And when we describe a matrix, we describe it to have a fixed number of rows and columns. In fact, let me actually just give you an example of a matrix. So let's say I have 17, 8, 3, 0, minus 3, 10, 7, 100, minus 100, and 8 again. So this is an example of a matrix, and conventionally we usually give them capital letter variables like capital A so that we know that it's a matrix and not a regular number. But anyway, this is a matrix, and this matrix A has 3 rows and 3 columns because I can count the number of rows and the number of columns. Now inside of this matrix we have these things, and these things are called entries. So let me type in entry. This thing is called an entry, and entries are just any old thing that go inside of a matrix, and they can really be anything, but usually they're just single numbers, plain old numbers, that what we're used to. And now when I draw this out, now we can kind of see why a matrix makes perfect sense to model an image. These entries kind of are like pixels, and the rows and columns are kind of like width and height. So we can have a better understanding of why do we prefer matrices to represent images. Now we can use this capital A to refer to the entire matrix as a whole, this entire grid of values, or what we can do is we can refer to a particular element of a matrix using this particular notation. And let me just write this out. For example, if I wanted to refer to this 17, this one that I just highlighted, that would be element A sub 1 comma 1 equals 17, and that's a true fact. So the way that this works is we have the first, these two things are called indices. Actually, let me just, indices. These things here called indices, and what they allow us to do is they allow us to access the individual entries of a matrix instead of having to refer to this thing as a whole. So this first entry here is at position 1, 1, and actually mathematically we start numbering matrices at 1 instead of 0 like we do in computer science, because when we get into things a bit later on, mathematically it just works out better if we start with 1 than we do 0, but so that's kind of something to keep in mind. But that's how we do indices here. So this first index, it refers to the row, and then the second index refers to the column. So it's in this format. So 1, 1 is the first row, first column, which is this entry here. So now what I'm going to do is, why don't we take a second, and I'm going to write down, we'll do this, we'll try to get a few exercises in here, where I'm going to write down an array entry using this notation, and why don't you take a second and pause the video and see if you can figure out which entry I'm referring to. So I'm going to write one here. I'm going to say 2 comma 1 equals, and then so now I want you to take a second and pause the video and see if you can figure out which one of these entries I'm referring to, and we'll be right back with the answer. Okay, so A sub 2, 1 means that I go to the second row, which is this row here, and then the first column, which is 0. So A1, 2 refers to 0. Excellent. So let's do this one more time and see if you can figure out which entry I'm talking about. So let's do something like 3 comma 2. And so I want you to take a second and pause the video and see, and we'll be right back with the answer. Okay, so when I say a sub 3, 2, I'm talking about the third row, which is this last row here, and then the second column, which would be this value here, which is negative 100. Okay, so now that you've got in kind of a hand of this subscript notation, I'm actually going to generalize this a bit so that we're not referring to, we can talk about any old matrix. So here, I'll just write generically that A sub I comma j refers to the ith row and the jth column. That's exactly what we're doing here. I just generalize it into something where we're not using specific values. Instead, we substitute anything we want. Just replace I with the correct row and j with the correct column, and you're appropriately referencing this entry. One thing to note, though, is that because A is a 3 by 3 matrix, there's no fourth row, or there's no fifth row, or fourth column, or seventh column. So you have to make sure that you keep this matrix I and j within the bounds of this this matrix here. This I and j indices have to be within the bounds of the A matrix. So now we're starting to see why matrices are a good mathematical way to represent images, because not only do they kind of look like images in this grid sense, but they also have all the properties that images do. Matrices have a fixed size. When we say a matrix is a 3 by 3 matrix, we're saying that it's always going to be a 3 by 3 matrix. We can't dynamically add rows or columns to a matrix. They have individual entries, and like I mentioned before, these entries are kind of analogous to pixels when we're discussing images. And they actually have also a similar coordinate frame. Notice that we start numbering up here at the top left, and I mentioned before that images also use the top left as their kind of origin point, except with images, when we're doing computer science stuff with images, we have to remember that we start at 0, but with mathematical matrices, we start counting at 1. So one more benefit to modeling images with matrices is that we can also formalize these image processing operations and algorithms as actual mathematical operations, which help us give some insight into why image processing techniques work the way that they do, and it helps us reason about the expected result of a particular image processing operation. And before we can delve into image processing, we first have to discuss some operations that we can do with matrices, and we're going to spend the next few videos discussing those. But to recap, in this video I discussed what matrices are, and they're just a 2D grid of values arranged in rows and columns. And this is actually similar to what an image is, right? They're just grids of values, and inside of this, the smallest indivisible unit is an entry for a matrix, or a pixel for an image. And then I also mentioned that how we can index matrices using this subscript notation of I comma j, where I is the row and j is a column. One important thing to note here is that matrices start at 1. So I'm actually going to put that in red here. So start at 1, not 0. Let me see if I can make that 0 a bit better, actually. We start at 1, not 0 up here. And in image processing and with computer science, we start with 0, but with matrices we start at 1, and that's how we can index to get a particular entry inside of this matrix. So like, for example, a sub 3 comma 2 is the third row, second column, and so we learned how to perform these indices. And so in the next few videos, we're going to talk about some of the operations that we can do with matrices that will help us when we discuss image processing.